In the previous class, we derived expressions for radius of the circular orbit in which electron is revolving around the nucleus, similarly velocity, and then we found kinetic energy, potential energy, total energy, and yesterday in the previous class we derived time period, frequency, angular momentum, magnetic moment and magnetic field induction as well as current, everything. But in all those derivations, we found that we used that electron is revolving around the nucleus in a circular orbit of radius r, and the charge of nucleus is Ze, charge of electron is minus e. So here the nucleus was at rest and electron is revolving around the nucleus which was at rest. But in general, actually speaking, the nucleus is not at rest. Even the nucleus also moves. So this is the electron, this is the nucleus. So electron moves around the nucleus like this. So this motion will be like this. So if it is the nucleus, if it is the electron, this will rotate like this. So this is just like a binary system in gravitation. So here this red color was the nucleus which is revolving in a particular orbit, and the electron it is denoted in a blue color, and both are moving with the same angular velocity. The angular velocity will not change. That means here if you join these two, this is the center of mass of this one, which is nearer to the nucleus as the mass of nucleus is more. Here I am going to write mass of nucleus much larger than mass of electron. So as the mass of nucleus is more, center of mass lies nearer to the nucleus. Now after some time, let us say electron comes to this point, nucleus will come to this point, then also this will be the center of mass. Now after some more time, electron, let us say it comes here and the nucleus will reach this point. So then also center of mass lies at the same point. So the common center for electron and nucleus is at point O. So I am denoting this point with O, and which is at rest. This point never changes. Both electron and nucleus revolves in circular orbits which lies in the same plane and the common center. So plane is same, just like this board. So here nucleus, this is electron. So they are revolving like this in two different orbits. Both revolves in the same angular velocity in the same sense. Let us say it is rotating in anti-clockwise direction. The electron also rotates in the anti-clockwise direction. If electron moves in clockwise direction, nucleus will move in the clockwise direction only. So they are having same sense, same angular velocity, same center, common center, and the center is at rest, and they are orbiting in two different orbits. Now from this I am going to find out the radius of the orbit of the electron and the radius of the orbit of the nucleus. So for this what I am going to do, I am going to find this is center of mass formula, which is equal to xcm is equal to m1x1 plus m2x2 by m1 plus m2. Now the distance or the radius of this red color orbit, so this I will take it as Rn, that is the radius of nucleus. So this is a Rn, and radius of the electron orbit from center of mass to here, let us say this is Re. Now how to find Rn and Re? So we studied this in center of mass in the first year system of particles in rotation motion. Here if you consider this is the origin, then what is the center of mass ordinates here? Now I can write xcm is equal to m1 x1 plus m2 x2 by m1 plus m2. xcm is this one, and let us say this is the origin here. This is nucleus is at origin. So xcm is equal to, from here to here this distance is Rn, that is the center of mass for these two, nucleus and electron. This distance is Rn from this origin. This is equal to mass of nucleus, that is Mn, into, as it is origin, let me take x1 as 0, and this is mass of electron Me, and the distance of this one from this, because this is along x-axis. So this is Rn plus Re, this is Rn plus Re by, this is Mn plus Me. So this is Rn, that is radius of the nucleus orbit is, so I am going to write Rn is equal, this will become 0, mass of electron into Rn plus Re, that is from here to here. So let me take it as R here, distance between the electron and nucleus, and this value remains constant. It comes here at any point R is constant. So let me take it as R by Mn plus Me. Similarly, what is the radius of the electron orbit? This is given by mass of nucleus into distance between the nucleus and electron by Mn plus Me. Now we can write the ratio of the radius of the nucleus to the radius of electron is equal to this by this, as denominator get cancelled, RR get cancelled, we can write mass of electron by mass of nucleus. So when the mass is more, this radius will be less. Here mass of nucleus is more, so radius of the nucleus is less than the radius of the electron orbit. So this is the relation between radius of nucleus to the radius of the electron orbit. Centripetal force required for the electron to move in a circular orbit. The centripetal force is given by centripetal force, which is equal to Cf, that is mv square by r or mr omega square. So as I am finding centripetal force of electron, this is mass of electron, radius of electron, square of the velocity of angular velocity of this electron. So this is given by, this centripetal force is provided by the force of attraction between nucleus and electron. So this I am going to write as 1 by 4 pi epsilon naught Ze into E by this distance between these two is R square. So now you can write mass of electron into what is the radius of the electron orbit. Radius of the electron orbit is mass of nucleus into distance between the electron and the nucleus by mass of nucleus plus mass of electron into this omega square is equal Ze square by 4 pi epsilon naught R square. So from this we can write, you can keep this omega square here. So omega square is equal Ze square by 4 pi epsilon naught R square, and other terms if you bring that side, this will become Mn plus Me by Mn into Me, this is Me into Mn into R square, you can write R cube here. So this omega can be written as the square root of this one. So angular velocity of both nucleus and electron, angular velocity omega is given by, you can see this equation, Z is a constant, E square is a constant, 4 pi epsilon naught R cube. Remaining terms, sum of the nucleus and the electron masses by product of this one. So here I am going to write this as mass of nucleus plus mass of electron by mass of nucleus into mass of electron. So omega can be written as root over Ze square by 4 pi epsilon naught R cube into mu here. Mu is nothing but mu is equal to Mn into Me by Mn plus Me. This is called a reduced mass of the system. So here mu is the reduced mass of the system. Now we know that the value of mass of nucleus, in nucleus as it is hydrogen atom we have only one proton. This is mass of electron, and sum of these two, this will be very negligible value. So this is called reduced mass here. The electron and nucleus revolve around each other, the total angular momentum must be conserved. Total angular momentum of the nucleus as well as electron, because both are revolving in different circular orbits. So what is the total angular momentum? L is given by mass of nucleus, radius of the nucleus orbit, mr square into omega, because angular momentum is equal to mvr, m into r omega into r. This is mr square omega. For nucleus, mass of nucleus, radius of nucleus square by omega, plus for electron, this is me re square omega. So now I am going to take mn common, rn square omega common, multiply with 1, you will get the first term. Second term, I need me, so multiply with me by mn. If you multiply these two, you mn get cancelled, you get me, and this will be re by rn whole square. Now once again, if you multiply this, rn square get cancelled, you get re square. This is equal to, this must be equal to, we know that according to Bohr's angular momentum conservation, the total angular momentum of electron must be equal to nh by 2 pi. So let me take it as nh by 2 pi, where n is the orbit number, h Planck's constant is 2 pi. So from this I can write mass of nucleus is constant rn square omega into 1 plus me by mn. But what is re by rn? Here I have re, here we have rn. Re by rn is equal to denominator get cancelled. So this will become mn by me. This is mass of nucleus by mass of electron whole square. This is equal to nh by 2 pi. Now this can be written as mass of nucleus, radius of nucleus square omega. Now you can see this is me, this is me square. This is mn, this is mn square. So these two get cancelled. This and this get cancelled. This and this get cancelled. The remaining terms are mn by me. So 1 plus mass of nucleus by mass of electron. This is equal to nh by 2 pi. So from this we can write, you can take the LCM here. Mass of nucleus, radius of the nucleus orbit, this is equal to, by taking LCM here, mass of electron plus mass of neutron by mass of electron into, this is equal to nh by 2 pi. Now what is the radius of the nuclear orbit? That is nothing but me into r by mn plus mr. So let me take mn as it is, but rn is mass of electron, distance between electron and nucleus by, this is mn plus me whole square into omega into me plus mn by me is equal to nh by 2 pi. So what are the terms that can be cancelled here? So let me take this as mass of neutron, mass of electron square, r square by mn plus me square into omega into me plus mn by me. You can cancel this and one of this one, and me square m get cancelled, which is equal to nh by 2 pi. Now what are the remaining terms here? We have mass of neutron into mass of electron by mass of neutron plus mass of electron into r square omega is equal nh by 2 pi. For a single electron, the angular momentum is me r e square omega. For a single nucleus, mn rn square omega. But for this system, this is called, already we studied this as a reduced mass, which is equal to mn into me by mn plus mg. So whenever electron and nucleus are moving together in two circular orbits having different radii with a common center, then we need to take, while finding the angular momentum, we should not consider the mass of electron or mass of nucleus. We should take the reduced mass of the system, which is the product of the mass of nucleus and electron by sum of the masses of nucleus and electron into, this is the distance between the two particles, that is nucleus and electron, into omega. This is the actual angular momentum. But till now we have not considered the motion of the nucleus, but today we are considering nuclear mass is also concerned. Nuclear mass as well as nuclear motion is considered here. If you consider nuclear motion, then the mass will become, instead of mass of electron in each and every step you have to write reduced mass. Instead of mass of electron for angular momentum you have to write reduced mass. If a nucleus is at rest, we know that radius of the orbit in which electron is revolving. So the radius expression is r is equal to epsilon naught n square h square by pi m z d square. Here m is the mass of electron. So radius is inversely proportional to mass of electron. But here instead of mass of electron we need to take the reduced mass. So radius of orbit is equal to r is equal to epsilon naught n square by pi m z square. You can write this as r naught into n square by z. But if the nucleus is in motion, then the radius formula is given by r naught. Here r inversely proportional to mass of electron here, where r naught already we got this value. Epsilon naught n square by pi m e square is the r naught value. So now if you write this one, r naught into n square by z into, here instead of this mass of electron you should write here radius r dash inversely proportional to mu by me. So if you write this one, me by mu here, where mu is the reduced mass. Similarly, speed of electron is given by v is equal to z e square by 2 epsilon naught n h. In this expression there is no mass. That means whether nucleus is at rest or nucleus is in motion, the speed of electron remains as it is. Here also this is z e square by 2 epsilon naught n h. Since v does not depends on mass. So we will get the same expression for both cases here. Now what is the energy of this electron in the nth orbit? Minus m z square e power 4 by 8 epsilon naught square n square h square. So here energy directly proportional to mass of electron only. But here what happens, energy if you consider nucleus motion, so energy is given by minus of, in place of mass of electron we should write mu by me into, this will be z square e power 4 by 8 to epsilon naught square n square h square. So here this is the energy if you consider nucleus mass motion. Now wave number is given by 1 by lambda is equal to r into z square 1 by n1 square minus 1 by n2 square. But here this wave number 1 by lambda dash v dash this dash r dash, this is given by, as r also depends upon the mass of this one. Why? Because this is m into z square you will get. So this will become mu by me into r into z square this r into z square into, this is 1 by n1 square minus 1 by n2 square. So if you consider the motion of the nucleus, then these expressions will change like this. Here consider a particle twice the mass of electron having same charge of electron revolving around a proton. So this is a proton here, and electron is revolving around the proton like this. But here we should consider the motion of the proton also. This is a proton and this is twice the mass of electron. So mass will be 2me, but charge will be E only here. Now find the minimum wavelength radiated in the Balmer series. In this for Balmer series we know that for Balmer series, as we are finding minimum wavelength is obtained for minimum frequency or maximum transition. So for Balmer series, minimum wavelength lambda is minimum means frequency must be maximum. Frequency maximum means change in energy should be maximum. Change in energy maximum means the transition is a maximum. Highest transition. That is for Balmer series, any electron in the high range orbit should jump to the second orbit. So here for Balmer series, for minimum the n2 to n1 should be infinite to second orbit. So this is also called series limit minimum frequency, minimum wavelength. Now I am going to write this expression 1 by lambda dash is equal, actually 1 by lambda is equal to r into z square 1 by n1 square minus 1 by n2 square. If the motion of the nucleus is not considered, we used this formula in PUC. But here in common exam, if the motion of this proton is considered, or here the nucleus is nothing but a proton only, 1 by lambda dash will become mu by me, that is reduced mass by mass of proton to r z square with this one. So 1 by lambda dash is equal, what is this mu? Mu is given by mass of that particle 2me, mass of proton mp by mass of the particle plus mass of the proton. Here mass of the electron is very very small, so this can be neglected, and if you neglect this one, nearly 0, this mp get cancelled, this will become 2me. So I am going to substitute here mu is equal to 2me by mass of electron me into r into z. Here we have only one nucleus, that nucleus consists of only one proton, so z is equal to 1 by 2 square minus 1 by infinite square. So this me get cancelled, the effective Rydberg constant will become 2r here. So this, from this we can write 1 by lambda is equal 2r into 1 by 4 minus 0. So this will become 2r by 4 or r by 2. So lambda is equal to 2 by r here. This is 2 by r is equal to 1.089 or nearly 1.9 into 10 power 7. So this 2 by 1.09 into 10 power minus 7. So 2 by 1 is nearly 2, but as the denominator is slightly greater than 1, so this lambda dash is equal to around 2 by 1 means around 1.8. 1.8 into 10 power minus 7 or 1800 angstroms. So this is not exact value, nearest value. So by checking the options you can find the nearest value here. Excitation of atom by collision. Suppose if you take any one hydrogen atom, this is the nucleus of hydrogen atom, and this is the first orbit, n is equal to 1, and let us say one electron is revolving here. For this electron to excite to the second energy orbit, n is equal to 2, or higher energy, any higher energy orbit, n is equal to 3 or n is equal to 4. For this electron, we need to supply some energy. So we can supply this energy in any form. Let us say, if you take a particle, either it is electron, proton, neutron, deuteron, alpha particle, any particle, when it collides with this one with a velocity v, then what happens? Due to this collision, there will be some loss of Ke for this particle. Due to that loss of Ke, this electron will gain that energy and excite it to the higher energy orbit. Now, for two particles of masses, let us say this is m1, this is m2 here. What is the loss of Ke? In first PUC collisions, we studied this loss of Ke as half into m1 into m2 by m1 plus m2. This is the reduced mass of the system into u1 minus u2 whole square into 1 minus e square. This is the loss of kinetic energy in a collision. So here also there is a collision between a particle and an atom here. Now, this loss of Ke is given by half into, if the masses of these two are same, let us say this is also electron here. If a high energetic electron collides with another electron here, then this will become mass of electron into mass of electron by mass of electron plus mass of electron into u1 minus u2 whole square into 1 minus e square. So this you can write half into me square by 2me u1 minus u2 whole square into 1 minus e square. this me get cancelled. So this is equal to half into mass of electron into, this will be u1 minus u2 whole square. Let us say this is a perfectly inelastic collision. For perfectly inelastic collision, that means after collision, both the hydrogen atom and this electron moves together with the common velocity. For perfectly inelastic collision is equal to 0 here. So what is the maximum loss of energy? So loss of Ke maximum. So particular system loses maximum kinetic energy in case of this perfectly inelastic collision only. So this is given by half into me into u1 minus u2 into 1 minus 0 square become 1. So this is u1 square. As this is at rest, here hydrogen initially at rest, u2 is equal to 0 and this is u1 here. So this can be written as 0 square. This velocity is given as v whole square. So this is half mv square. Here me by 2 is there. So this is 2. So this is half into half mv square. What is the initial kinetic energy of electron? Here before collision, Ke initial is equal to half me v square. But after collision, if it is perfectly inelastic, this final loss of Ke is this much, remaining Ke will be Ke final is equal to initial Ke minus final Ke, that is half me v square minus 1 by 4 me v square. This will become 1 by 4 me v square. So final kinetic energy in this case is nothing but initial kinetic energy by 2. It is given that this electron which is having 24.5 electron volts of kinetic energy striking this one, and if the collision is perfectly inelastic, what is the effect of this collision? Due to this effect, the final kinetic energy given by final kinetic energy is equal to half of the initial kinetic energy. So this can be half into, what is the initial kinetic energy? This is equal to 24.5. So this is a 12.25. So during this collision, this electron which is having this much energy will lose somehow half of its energy, and remaining half of it will be lost. That last energy will be gained by this electron. So by using this energy, so energy gained by this electron, revolving electron, energy gained by revolving electron is equal to the total energy of this electron is 24.5. In this it lost 12.25. That last one will be gained by this one, which is equal to once again 12.25 electron volts. Now we know that for this electron which is orbiting in the first orbit, energy 30.6 electron volts. Here this energy will be 30.6 by 4. So this is your 3.4. So what is the energy difference between these two? 10.2 electron volts. So when this electron gains this much energy, now it can jump from here to which orbit? The energy difference between these two is equal to 13.6 minus, this is 13.6 by 9, 1.5. So this will be 12.1. So this is more than 12.1. That means this electron can jump up to this third orbit here. So this is called excitation of atom by collision with other particles. If collision is elastic, let us say this is the particle of mass m having kinetic energy k naught. It collides with an atom, hydrogen atom only. Here mass of this one is m, and this n is equal to 1, which is initially at rest. Now before collision, this is the situation. After collision, what will be the situation? So as it is a elastic collision, there is no change in kinetic energy. Mass this one, velocity let us say v1, and this one mass is also m, and let us say this velocity is v2. So first let me find out, let me apply law of conservation of linear momentum. So before collision, this is before collision, this is after collision. So linear momentum before collision must be equal to linear momentum after collision. So here it is initially at rest, so momentum will be 0. Here it is moving, so momentum is given by, we know kinetic energy. So Ke is equal to P square by 2m. P is equal to root over 2m K naught. This is the linear momentum of the system before collision. After collision, this will become m v1 plus m v2. Otherwise, you can write this as m1. See, this is m2. This mass, let us say this is m1. So you can write m1 v1 is equal m2 v2. This is a law of conservation of linear momentum. But we know that in elastic collision, change in kinetic energy or loss of Ke is 0. That means total kinetic energy before collision must be equal to total kinetic energy after collision. So kinetic energy before collision, this is K naught. So this is K naught. For this, as it is at rest, it will 0. And what is kinetic energy of this one after collision? Half m1 v1 square plus half m2 v2 square. So here, this is the total kinetic energy before collision. This is the total kinetic energy of the system after collision. This is the particle kinetic energy. This is the hydrogen atom kinetic energy. Suppose if the collision is inelastic, that means there will be some loss of Ke for this particle, that energy will be gained by electron. Due to this, it may do some transitions here. It may make transitions. Now, before collision, let us say this is m1 having kinetic energy K naught, and this is the atom. Initially, this is at rest, and n is equal to 1. Mass of this is atom is m2 here. Now, for this after collision, as it is inelastic collision, so there will be loss of Ke. Ke will be lost here. Ke is lost. Now, after collision, let us say this is m1 moving with the velocity v1. This is m2 moving with the velocity v2 here. First of all, let me apply law of conservation of linear momentum. Whether it is elastic or inelastic, we can apply this law of conservation of linear momentum. That is initial momentum of the system as it is at rest. Momentum is 0. For this root over 2m Ke, K naught is equal. After collision, this will be m1 v1 plus m2 v2. So whether it is elastic or inelastic, this remains as it is. But what is the change in kinetic energy? Before collision, the total kinetic energy is K naught. After collision, kinetic energy is half m v1 square plus half m v2 square. So total kinetic energy before collision is equal total kinetic energy after collision, that is half m1 v1 square plus half m2 v2 square plus energy required for excitation, because this electron jumped from first orbit to second orbit. For any electron in a hydrogen atom to excite from first orbit to second orbit, the energy required delta E is given by energy of the second orbit, which is equal to 3.4. Energy of first orbit, this is equal to 30.6, or 30.6 minus 3.4. So this is 30.6 minus 3.4, that is 10.2. So this value will be 10.2 electron volts. So from this we can write initial kinetic energy of this charged particle minus 10.2, because in this it will lose this much energy for this electron excited from first orbit to second orbit. This must be equal to the sum of the kinetic energies of this particle as well as this atom after collision. Similarly, in the third case, if it is from first orbit to third orbit, directly I can write this will be root over 2m K naught remains as m1 v1 plus m2 v2, but this formula K naught will be half m1 v1 square plus half m2 v2 square plus, for the electron to jump from first orbit to third orbit, first orbit energy is equal to minus 30.6 electron volts, third orbit energy is equal to minus 1.5 electron volts. Difference between these two will be 12.1 electron volts. So this minimum energy required for this electron to excite from first orbit to third orbit is this much. So from this initial kinetic energy in this, it loses 12.5 electron volts energy, and this must be equal to half m1 v1 square plus half m2 v2 square. Electron with Ke 10 electron volts instead in a hydrogen atom in its ground state, the collision is. The total energy of the electron that is striking the hydrogen atom is 10 electron volts. For the electron which is in the first orbit to excite to the second orbit, the minimum energy required is equal to, this is 10.2 electron volts. But the energy given by this electron is only 10 electron volts. So this electron cannot excite to the higher energy orbit. So this collision must be elastic collision only. Now, second problem. A photon of 10 electron volts energy collides with a hydrogen atom in its ground state. So this is the hydrogen atom in its ground state. So N is equal to 1, which is at rest, and electron is revolving here around the nucleus. And one electron, a photon here, a photon of energy 10.2 electron volts collides with the hydrogen atom in its ground state. After few milliseconds, one more photon energy of 15 electron volts collides with the hydrogen atom. What can be detected by the suitable detector here? In the first case, when the photon gives this much energy, this electron can jump from first orbit to second orbit. So due to this, once again it will stay there for a fraction of a second, and this electron jumps back, and this energy is equal to 10.2 electron volts. That means we will have some radiation which is in the form of photon itself. But after few milliseconds, in this case, one more photon of energy 15 electron volts collides with this hydrogen atom which is initially at rest. So here, what is the minimum energy required for the excitation? From here to here, first orbit to second orbit, minimum energy is equal to 10.2 electron volts. But if it jumps to second orbit, third orbit, fourth orbit, fifth orbit, up to infinite orbit, this energy is equal to minus 13.6 electron volts in the first orbit, and in the infinite orbit, energy in the infinite orbit is 0. So what is the energy difference between this and this? The energy difference is energy difference in the infinite orbit minus first orbit is given by 0 minus of minus 13.6, which is equal to 13.6 electron volts. That means from one orbit to another orbit, the transition is called excitation. If this electron reaches the infinite orbit, that is called ionization, because this electron will leave this infinite orbit and goes outside with this supplied energy 15 electron volts. So for this electron to ionize, for this atom to ionize, we need only 13.6 electron volts. But what is the remaining energy left with this electron? This electron which is jumped to this higher energy orbit, 15 minus 13.6, so 1.4 electron volts. This electron, after jumping to the infinite orbit, it comes out with a kinetic energy of the difference here 1.4 electron volts. So here the detector will detect that it will detect a photon plus and electron with Ke which is equal to 15 minus 30.6, that is 1.4 electron volts energy. So this detector will detect two things. One is photon, other one is photon of energy 30.6 and electron of energy 1.4 electron volts. Sometimes they may ask you to find out the de Broglie wavelength of a neutron. The de Broglie wavelength lambda is equal to h by mv, that is also equal to h by p, h by root over 2m ke, h by root over 2m vq. So these are the different formulas. Now, as a neutron has no charge here, so we cannot use this formula because charge will be 0, and even kinetic energy related to work done VQ, so we cannot use these formulas. Then we have the translatory kinetic energy in translatory motion that we studied in kinetic theory of gases in first PUC, which is equal to 3 by 2 kT. Now, in place of Ke, instead of Vq, we can write this formula also. So what is the de Broglie wavelength for a neutron? For a neutron, the de Broglie wavelength is given by h by root over 2m, where m is mass of neutron. Ke is equal to 3 by 2 kT. This T2 get cancelled. De Broglie of neutron is equal to root over 3m kT, where T is the temperature, K is the Boltzmann constant, m is the mass of the neutron here. Similarly, suppose if you take one photoelectron, what is the de Broglie wavelength for photoelectron, which is given by h by mv here. So this is h by root over 2m ke. mv is equal to, momentum is equal to root over 2m ke. For a photoelectron, we know that E is equal to 5 plus ke. So ke is equal to E minus 5. So lambda photoelectron is given by h by root over 2m into, this will become E minus 5. This is the de Broglie wavelength for a photoelectron. Similarly, let us say one charged particle is moving in a magnetic field B here in a circular orbit of radius r. So what is the de Broglie wavelength for this one? This lambda is given by h by mv here. Here, as this is moving in a circular orbit of radius r, we know radius is given by mv by bq. So what is mv here? This is equal to bqr. So here you can write h by bqr. This is the de Broglie wavelength of a charged particle moving in a circular orbit of radius r in a magnetic field B. Now, we know that for a hydrogen atom like this one, when the electron is revolving inside this one, we know lambda is equal to h by mv. But we know that the angular momentum of the electron which is revolving in a circular orbit of radius r is given by lambda, this angular momentum L is equal to mvr is equal to nh by 2 pi. So from this, what is mv here? This lambda is equal h by, this mv can be written as nh by 2 pi r. Here h and h get cancelled by cross multiplication. The circumference of this circular orbit in which electron is revolving always equal to integral multiple of lambda, n lambda, where n is number. So if this electron, when it is revolving, it not only acts as a particle, it acts as a wave. So this wave number, this is one wave here, second wave, third wave, fourth, fifth, sixth, seventh. So here it is a 7 lambda. For another one, it may be 8 lambda, 9 lambda. That means. So this is a 2 pi r.